Hello, hi. So today I have picked the one more interesting problem, which is to design the generic priority queue. This is the interesting one. This problem is well, I was also asked in the Amazon interview. So let's jump into the problem statement first. So let me just explain the problem statement. So your statement says like designing and implementing the reusable priority queue library similar to Java inbuilt priority queue. So this would be a generic and extensible, and this should support also like storing the any type of object. So that's why it's saying like make a it's generic, and also it's allow like a user can define its own like ordering using the custom comparator. And the functional requirement is like similar to the uh, inbuilt priority queue, which is the offer, poll, peak. This is the similar like standard one operation of the priority queue. Size, empty, and clear. Okay. So to other operation, which is the new one to this custom priority, we need to implement it. Like delete an element means remove an given element and check given element exist in priority queue or not. Okay. Ordering is like it can be max, minim behavior based on the user provided the comparator, and it also support the duplicate element. And dynamic capacity means priority queue should automatically grow when it's become full. So if you ever think about the Java inbuilt internal algorithm, it's also do the same thing. So we need to do the same logic for our custom priority queue implementation. Okay. Heap construction is like it should support like we are when we passing the collection of element, it should build heap from that first. Okay. Update a priority efficient. Efficient update the priority updates means for a existing element means for any custom object which we have added into priority queue, this should support the update priority means after adding it we will able priority queue able to update that uh, task with the new priority. Okay, that need to support that. Expected performance for these all these operation is mentioned here, like offer, poll, remove, priority, update the priority. All these three operation four operation will be the in logarithmic, and other will be the constant, except this one build heap from, which is also like linear time complexity. And constraint is mentioned like we should not use the inbuilt priority queue implementation. We can use the appropriate collections, and but heap implementation must be your own. Okay, so let's uh, jump into the design and think about the how we will implement it. So priority queue is like either it will be the max or min heap. So it's a heap data structure. Okay, heap data structure, which is the complete binary tree. Complete binary tree. If you have ever remember what is the complete binary tree is like where the all level of the tree is completely filled. So it's a binary, so it's have at most two children, but all the label of its all the label it's completely filled except last one. So that's why it's provide the height of the binary tree is logarithmic. Okay, that's it guarantee by the complete binary tree that the utilized by the heap data structure. So min heap the priority is like each parent, each parent node value should be is less than or equal to the its child value for min heap. And for max heap this is opposite one, like each parent value should be greater than equal to its node value. Okay, and it's represent at in array structure at which is also compact, so it is like cache friendly due to the continuous indexing, that the also an advantage. So first I have written the some operation with their desired complexity. We need to think about it. So all these four operation would be the logarithmic, and other would be in the constant time complexity, except the building the heap from the provided the collection. So first let's jump into the how we will do for each operations. So I have written down for any problem statement. First, you will need to write down what are the operation and how will you do, and what are the already inbuilt data structure that we can utilize in that. Okay, so that's the way you can think about that. So for as I mentioned, like heap is represented in the form of array structure. So for any index, ith index, parent of that index would be at I minus 1 by 2 position, and child left and right child would be the at this position. This is the formula, mathematical formula for that, for this one. Okay, so native operation is like add element. So in add element, first initially, if you think about the initially, size would be the priority queue size will be the 0, means no element exists so far. Okay, so first I will append add end, which is size is means adding at 0th index, append at the end of array, increase the size. At this point, is it hold one element, then it will increase the size, which is 1. So after adding any new element to the priority queue, we need to do the like sift-up operation, which will ensure that this property like parent, compare it with the parent until compare it with this parent and swap until the property is violated. Which property? Means parent should be less than or equal to its child for the min heap. That the property should be need to check for each uh, index with its parents. And this operation will give the time complexity of logarithmic due to the complete binary tree property. Like, so if we have think about like we have like divided uh, all the elements into like level 1, if you ever like think about the level 0 have one element, level 2 have two elements similar to the power h, if where h is the height. So that the formula is derived from. And in pole operation, we first need to swap the topmost with 0th index with the last one and decrease the size. Then do the heapify, means start from uh, uh, top element to the bottom and return the deleted element, which is the also like logarithmic time complexity. Peak and size empty, just need to check peak for just need to check 0th index, size empty, but we need to check the size. Okay, special operation that we need to support the like remove element. So as of now, if you think about the initially uh, we have only one access, like first one element, right? First means the 0th index element. We don't know which element is it, but we we know that it either it will be max one, either it will be minimum, right? We don't know what is the element. But for a remove element, if we like give an element, we iterate the entire the array, then it will be like log give the time complexity of linear time complexity number of element present in that array. But we need to do in like logarithmic. So we need to like store somewhere so that we can get index value of that element. Okay, so think about the how you are doing the pole operation, right? In a pole operation, if you think about the in pole operation, you are removing the 0th index. So that extension of this pole operation, like in remove operation, we need to remove ith index value element. Okay, so we have a element, if we have store somewhere, so that we can get the index value of that given element in constant time, then we can do the same like a pole operation, right? So we have already inbuilt inbuilt data structure as map that can we can utilize that, where we can store the element as a key and set of integer means why we need set first. Like let's think, we have a we are supporting the duplicate element, right? So same element can be present at anywhere, like index 1, index 5, index 6, like. So we need to like add all these duplicate all these element, all these index for that element, right? So that's why we are making the like set of this one. So similarly, like pull on for there is one twist, like if you think about like deleting at zeroth, which is pool, right? Zeroth element where we are doing in pool operation. So for zeroth element, we don't have any parent of this index. So we are only performing the sift down operation, right? We are only comparing its child. But in remove operation, we can either get any index value, which may have its parents also, may have its child also. So we need to check, either we need to do the shift up, either we need to do the shift down. Okay, so how we will decide? For ith index, first I will swap it with the last element. For ith index, swap with last element, then last element will come at ith index, right? Once you swap it, then this need to check its parents. If current swap means current value as ith index is smaller than its parent, then we will go to the shift up operation, either we'll go the shift down operation. That's the logic. So in that case, we are checking, it can be either shift up operation, either it can go shift down operation. Okay, so that's the things we need to make sure about. At contain operation is simpler. So we have already maintaining the hash map for the uh, get for a fetching a index for the in a remove operation. So we have already like storing that. So we just need to check whether it exists in a hash map or not. That will be the constant time complexity. Okay, for uh, com comparison comparator. So let me tell you, for primitive type data structure, we have like wrapper classes, integer, long, string, characters. These are the inbuilt, which already comparable interface. Okay, so for any custom classes, we have two option. We have means user have two option to provide. So we just only support that option, but user responsibility for the custom class object, how it will be the like make comparable, right? So first option is like define a student, like we are creating the priority queue of the student class. So then student class is already implement the comparable interface, then it will provide the compare to method. So it will provide the compare to methods, then our priority queue will use that method, right, to decide whether it's so it is smaller or larger. Okay, but it's less flexible, right? Second option is more flexible, which is the pass the comparator while defining the priority queue. So whenever you define the priority queue, we can pass the comparator. Like there are two objects we need to compare based on this one. So this our priority queue will also have a variable for the comparator. So if we have a comparator, we first give the priority for the comparator. If not have, then we will fall back to that comparable methods. Okay. So this is our will be our comparable logic. If first we have a comparator, user have passed the comparator, then we will just use that comparator. Otherwise, we will fall back to the compare to method. Okay. And problem statement doesn't show about the like doesn't mention about anywhere in like concurrency, like thread safety. So if you ever encountered like how will you make sure like thread safety for these operations, you can mention the retrant log. You can take a global retrant log, and for each method you can apply that. Take a retrant log, and once all the operation done, you can release that. So for the more detail about the how retrant log implemented, how it's work, then you can check out my the LRU cache design video where I have mentioned the all the perspective of thread safety related things. So let's jump into the implementation part where I will show you the how it will be implemented. So I think before jumping into the implementation, let me show you how it's works in with the with the given example. Hello, so I will show you the with the given example. I have taken the array of eighth element, and I will show you how it will work when you will add a element in a priority queue. So first I will insert the initially array size priority size is a 0. So initially it have a 0 element in a priority queue. So I have taken an array. Initially it is empty, and also I have initialized the to visualize better. I have draw the like tree structure for this one, and which I have in for each node I have index with each uh, level from start from 0 to till 14. Okay, so let's first insert the 45. So initially no element as so far in PQ, so insert it at 0 element. So it is 45 if you see this value, and I will insert this one also at this place. So as of now only one element, so no need to apply the sift-up operation. So let add another element which is 12 at index 1. Once you add another element, it have a greater than one size of priority queue. And so we need to do the shift operation. We need to check with the current index value is smaller than its parent, then we will need to swap it until it's property violated. Okay, so if you find out the parent of this index, so 1 minus 1 is equal to 0 by 2 is equal to 0, which is 0th index. So we need to swap with its parents because it is higher value. So let's swap it with the 55. Okay, and I also do the same things here. Okay, so let add another value which is at index 2, which is just 72. Okay, 78, not 72, and let add 78 here. So if you see 78, then you will see like you need to check whether it is smaller or greater than its parents. What is the parent of it? 2 minus 1, which is 1, 1 by 2. If you This is formula, you can find out the which is the parent of this current index. So if you apply this formula, that will be give the 0, right? Which is smaller, already smaller. So let's add a 3. When you add a 3, add index 3, and if you find out the parent of index 3, then it will be 1, which is greater than the it's the child. So we need to do the swap operation here. It will be swap with this uh, 45, right? Then again we need to check whether it violated property mean heap. It will already it is also violated with its parents. Index 1 parent is index 0, then we need to swap it again with its parent. So now this is perfect, right? So let add another value is 56 at index 4. 56. Once you add a 56, you will see let me add a 56. I will need to just modify here also, which is Let me just hit a 12, hit a 45. Is it? Once you add a 56, add index 4. Let me find out what is the parent of it. Parent of it, if you find out, apply this formula, you will get a index 1, which is already smaller, right? So we don't need to do anything. So just add another value at index 5, which is 90. Let me add a 90. Okay. Once you add a 90, add a 90, we need to check again. 5 minus 1 is 4 by 2 is equal to 2. So that is smaller, already smaller. We don't need to do shift up operation. Let's add index 6, 21. Once you add a 21, add index 6. Okay. 21. Let's find out its parent. Index 6 parent is a index 2, right? And once you compare it, it will be higher, right? So we need to swap it with its 78. And if you find out again, check with the this one, which is 0, which is already satisfying. So we need to swap with 21 with the 78. Okay, let add another value, which is 8 at index 7, right? 8. Once you add a 8 at index 7, now size is 8, priority queue size is 8, right? So let's find out the its parents. 7 minus 1, which is 6 by 2, which is 3, which is smaller than the this one, right? Let me just do the, what is the value of this one? 45, right? 45. So index 3 has a 8 and index 7 has a 45. Now let me check again. It's, if you check it again, it already it's now it's violating all, right? So let me do that again, swipe it again. Let me check again, it's with its parents. Now its parent is smaller, already smaller, so we don't need to do, just stop here. So now if you see all the parent, which is 3, is smallest among all its children, right? If you see this one, if you see this one, this is smaller among all this child one node. If you see this one, all this is smaller this child node, right? Similarly this one. Okay, so now this is the way we add a new element into a priority queue and we do the shift up operation, okay, until it violated. For pop operation, but we just need to, what we need to was need to smallest one replay swipe with the last element. So let's 70 here, 45, right? 3. Okay, similarly let me do the change here also with the 3. Now make it we will decrease the size. Now size become the 7 and index become the 6. So let make it null. Okay, remove here from here, remove from here. Now do the shift down operation. When you do the shift down operation, you will check with its child. So you will replace swap with the smallest one, which is the 8, right? So let do the 45, swap with the 8. Then you get here, you reach here. And once you reach here, you will again check with its parents, left and right, which is the smallest, you will uh, swap with that. So here is the 45, here is the 12. Okay, now it's in correctly each parent has a smallest one. Okay, so this is the way how it's works. Like once you add once you poll, you do a poll operation, you do the shift down operation, you once you add, you do shift up operation. Okay, so let's jump into the its implementation, how we have implemented it here. So let me just okay, so I have already written a code here. So this is the my priority queue. I have make it generic. You can pass so that it can pass the any type while initializing the priority queue. So this is what I have discussed. I have taken the hash maps where I will store the indexes for the given key while adding a new value into a priority queue. Comparator value which will store the comparator passed by the user to compare the value. Okay. And default capacity I have taken the 100 one. You can take any. So I have defined 4 or 5 constructor method. One is the collection. Once user pass the collection or collection, we need to first build the heap, like min heap or max heap according to the constructor, according to the comparator. So this is the if you think about the this is the like fluid morph fluid algorithm, fluids algorithm. Okay. So this give the time complexity of we go from instead of n into log n. Okay. Suppose if you inserting one by one, so this will give this complexity. But if you are do the in place operation according to the fluid, it will give the linear time complexity. Because for suppose this logic is like if we have n size array, n size, let me just write down here, n size array, then for n minus 1 index, parent would be the n minus 1 by 2, which will be the n by 2 minus 1. So start from here till 0, do the heapify operation, in sift-down operation. That's the logic. So there are different constructor also, method also for capacity. First I will checking the capacity should be positive one, and also defining the array and hash map. And here also taking the comparator. User can pass its own comparator. So this is the one. First I will tell you the logic of the offer method where we add a new value to the priority queue. Okay. So offer first we will check the if value should not be null. If it null, it will I will throw exception. Either I have told you first I will add a value, then will I increase the size, and also adding the index of that value into a hash map so that I will get the value when we need to delete or check. Okay, do the shift-up operation. It is simple shift-up operation. If we will check the shift-up operation, it will first compare with the parent. If current value is smaller than parent, then bubble up means swap with the parent until it will violated. Okay. Ensure capacity while adding a new element into a priority queue. It can be reached to the like capacity means it become full. Then we need to check that if size be equal to the capacity, then we are adding a double of this size and creating a new array and copying the existing one, overriding with this reference. Okay, so just we are like making a double size of new array and copying the existing one when it reaches to the capacity. Okay, so in poll operation, we are as we discussed, we are just swapping the first means topmost element, the last one, and remove the last element from the hash map also, and from the array also, and do the shift down operation. In shift down operation, as I have discussed, like it will compare with its children until it violated. Okay, so this is new operation like remove and update. Once you get the remove, update is similar one and simpler one. For remove, first I will get the index value from hash map where we are storing index. Then we are doing the same as the poll operation, update swapping with the last one and deleting the last one. And once deleted, new means current index value having the last value, then we will need to check if it's smaller than the its parent, then we will go the shift up operation, otherwise we'll go the shift down operation. Okay, Similar for the update priority, get the index, then do the apply this same operation. So for other operation is simpler one. We are just checking the variable we getting in constant time. Okay, so this is the entire implementation in Java. I will uh, provide this implementation link, GitHub link in a comment box. You can ask me any doubts, any query if you have. So okay, bye, thank you.